So we're going to look at inequalities, and we're going to look at two types of inequalities, the techniques that are often used. One today we'll look at is using the idea of graphs, and then on Monday we'll look at the other idea. So inequalities and using graphs to solve inequalities. Now, I guess the very simplest type to do, and I'm not suggesting you would use a graph, by the way, to do this one, but theoretically you could. You get an inequality like this: x squared on x plus 2 is less than or equal to 1. So, I mean, you could draw up the graph. Now, x squared on x plus 2, well, there's x squared. I want to divide it by x plus 2. So I know there's an asymptote at -2. And there's our regions. We know there's an oblique asymptote. It'll be at x minus 2. There we go. There's x minus 2. And there's our graph. As I say, I'm not suggesting we would draw that up. But then we've also got y equals 1. And so what we're really saying is, when is that blue graph below my horizontal line? Right? And that would give us our solution. Now, the reason I'm saying this is not a great way of doing it is, unless you've got an incredibly accurate graph, which in this case I do happen to have, the points of intersection could be difficult to find. In this case, they do turn out to be whole numbers, and it worked out quite nicely. But otherwise, you'd have to go and solve the equation anyway. We get our two solutions, 2 and -1. So therefore, our solution is x is less than -2, or x is in between -1 and 2. I think the other way of solving that type of inequality that we're used to seeing would be better. But that is an example of using a graph to solve inequalities. Let's look at a more interesting type of question. Quite an old one now. It says, consider the graph y equals the square root of x. First thing they want us to do is to show that the graph is increasing, despite the picture. You know, obviously it is increasing. We can see that. Oh, look, it's going up. That's not good enough for a proof, of course. You can't say, oh, look, it's going up. We need to use our derivative, because we know that a curve is increasing when the derivative is greater than 0. So our derivative is 1 on 2 root x, and that's certainly greater than 0 whenever x is greater than 0. Thus, this is always increasing. And just to really confirm a point here, I've gone, well, I know at x equals 0, y equals 0. When x is greater than 0, y is greater than 0. So our curve is continually going up. Let's look at the inequality part. We're now going to show, and it says hence, so they're giving you the big hint, hey, use that graph, that the square root of 1 plus the square root of 2 plus and so on up to the square root of n is always greater than or equal to the integral of root x dx, which happens to equal 2/3 of n root n. So the idea is, if you remember when we first started with integration, we talked about inner rectangles and outer rectangles. So it's basically using that idea. Because we're trying to show it's greater than, it would be the outer rectangles that I'll be using, because the area of those outer rectangles will clearly be greater than the area under the curve. Right? And so as it's always increasing, and so I've actually written that down, so when they look at my proof, they know where I'm pulling these numbers from. I'm finding the area of those outer rectangles, and each one of those has a width conveniently of 1. The height of the first one is the square root of 1, then the next one's the square root of 2, and so on until we get to the last one, the square root of n. So that's where we get our sum. And that's greater than or equal to the area under the curve, which of course is just the integral. And the integral of root x, when we do go and integrate it, sure enough, it gets to be the result 2/3 n root n. Okay, so we've proved that inequality. Now they want us to use induction, same series of numbers, same pattern, but now we're going to prove it's less than or equal to 4n plus 3 on 6. Okay, let's test for n equals 1. Left-hand side, square root of 1 is indeed 1. Subbing to the right-hand side, we get 7/6. But 1 is less than or equal to the right-hand side. Hence the result's true for 1. So my assumption will be that that series is less than or equal to the 4k plus 3 on 6 root k. We want to now prove for k plus 1. All right, let's go do it. It is a series type, so I'll rewrite it. Sum of k terms Less than or equal to, our assumption was 4k plus 3 and 6 root k plus 1. We're trying to show, what was it? 4k plus 7? Okay. All right. Well, I'm going to create one fraction. So common denominator is obviously 6. What I'm also doing is putting everything under the surd in the first one. So I'm making it an entire surd. So I have now got 16k cubed plus 24k squared plus 9k plus 6 lots of root k plus 1. Because I believe there was a common factor of root k plus 1 we're trying to get. Is that true? Okay. So if I could now factorise this to have a factor of root k plus 1, we're almost there. Well, I can't quite do it. If I divide that by k plus 1, I get a remainder of minus 1. However, we're not dealing with an equation, we're dealing with an inequation. So therefore, that, which equals, by the way, yeah, right, I forgot I put this line in. If we factorise this, we get 4k plus 1 all squared. Now I'll try it again. But in fact, that is less than the root k plus 1. Remember the idea, if I'm subtracting 1, it's got to be less than. Now I can simplify this surd. I've got k plus 1, 4k plus 1 all squared, and 4k plus 1 plus 6 is 4k plus 7, and that is indeed the result that we're looking for. Hence the result's true for k plus 1, if it's also true for n equals k, and once upon a time we used to write really long sentences like this. Last part of the question was this. We just proved two inequalities. We're now going to estimate the square root of 1 plus the square root of 2 all the way up to the square root of 10,000 to the nearest 100. So I guess this is now what you call a real world problem. Because, you know, often you sit there and you wonder, what is the square root of 1 plus square root of 2 up to the square root of 10,000 to the nearest 100. Okay. We have now trapped our series in between. Remember we showed it was less than 4n plus 3 on 6 root n. We did that with our rectangles. And we also proved it was greater than 2/3 n root n. No, that was the one we did with rectangles. The other one we did with our induction. I'm going to let n equal 10,000. And look, in the middle we get what we're looking for. So we do know that the value will be in between 2/3 of 10,000 root 10,000 and 4 lots of 10,000 plus 3 divided by 6, all times root 10,000. And if we work that out to the nearest 100, something amazing happens. They're both equal to 666,700 to the nearest 100. So if it's in between 666,700 and 666,700, it must be, I'm going to do another inequality. We're going to prove x is greater than sine x. I'm going to do it via a graph. That's the line y equals x. Remember, your horizontal axis is in radians. And remember, pi is approximately equal to 3.159265358 anyway. There's sine x. So basically, I want to prove that that blue line is always above that red curve for x is greater than 0. Now, yes, it looks like it, but that's not good enough for proof. I can't say, oh, it looks like it. So I'm going to prove it. Function x equals x, we know the derivative is 1 at that point. Y equals x has a slope of 1. Sine x, its derivative is cos x. Now, in between 0 and pi on 2, cos x is always going to be less than 1. So the slope of the red graph is always less than 1 in between 0 and pi on 2. Well, the first derivative measures how quickly it's increasing. So therefore, the blue line is increasing at a greater rate than the red one. So therefore, it must be above it because they are beginning at the same point, that being 0, 0. So we know that y equals x is increasing faster than y equals sine x, so therefore x is greater than sine x. Now, we know that once we go past pi on 2, sine never goes above 1. So clearly y equals x will always be above it at that point. So therefore, x is indeed greater than sine x and so on. All right. 10F has got some inequalities in graphs questions in our Patel.